Okay, as usual, I denote S always a K3. And G in the automorphism group of S, finite. So that's very important, actually. In all what I'm going to say, any automorphism is always supposed to have finite order. Then there is a group morphism. That I call alpha, from G to C, that send to an element here, alpha G, where alpha G is defined as follows, such that the action of G on the two form is equal alpha G omega S. So recall, just for the notation, that we denoted by, we have H0, omega 2S, and we be denoted by omega S, the 2-0 form that span this line. And so in that way, we have that im alpha, even, sorry, this is C star. I take the without 0. So im alpha is then a finite subgroup of C star, so it's cyclic. Okay, and we can put this all together in an exact sequence. So let the note maybe, let im alpha be equal mu m, equal the, where these are m root of unity. And then we can consider the following exact sequence. Well, you have G going surjectively to mu m. So this is a notation for the image. And here you have the kernel of this map that I call G0. Okay, so this is the map, as I said before, alpha. And so G0 is the kernel of alpha. So this means that, well, these are all the elements, G in G, such that preserve the two form, so as identity. And now we are ready to give some definition. If you look in the problem sheet I gave you yesterday, you kind of find of a small resume of what I'm writing here. So the only difference is that in the problem sheet, if you look, I denote it by GN, so there are different notation for that. But you can find this exact sequence also there. And this allows then us to give the following definition. So following definition, again, we have seen this a bit yesterday when we were discussing about the exercises. Take G in G an element, then first of one, G is called symplectic. Oh, G is called symplectic. So G is, as usual, in out S, called symplectic. If the action of G on the two form is identity. So this means that G is in G0 in that notation. Second fact, so G is called a non-symplectic. So it does not preserve the symplectic form. If G star omega s is equal to alpha G omega s, I will tell you something in a minute, and this alpha G is different from 0 and 1. Is a complex number. So alpha G is complex, of course. And purely non-symplectic. If you have that the action on the 2 form is equal to theta n omega s, where theta n is equal to a primitive n root of unity, and n is the order of G. So it acts by a primitive root of unity, and it's really the order of the element. Just, yeah. No, that's why, I mean, I wrote there. So you have your representation is there. No, that not happen. So I just could write in C star if you want. It cannot happen. It's an automorphism, so it cannot happen. Just some remark. So, also in this second definition, also in 2, alpha G is a root of unity. Because, remember, I am assuming that G is finite. Okay, it's an important property. Okay, it's a finite group, so G is a finite order. So this means it is a root of unity, but not necessarily primitive. So for example, you can have, we'll see some example, automorphism of order 4 that acts on period by minus omega s. So this is an example that is not purely non-symplectic, because minus 1 is not a primitive for root of unity. It's a root of unity, not necessarily primitive, but not 1 in any case. So we say in that case it's only non-symplectic. Observe that second fact, that if G is finite, and any element in G minus the identity, maybe I have always to be careful somewhere to the identity, but anyhow. Is finite, and for any G different from the identity, G acts purely non-symplectic. For example, then what happened? Well, in that case, this means that G0 is identity. Okay, G0 is identity, so this means that G is cyclic. Okay, so you know the structure of the group. Anytime you act purely non-symplectic, as I say, non-symplectic is not enough, of course, because non-symplectic you have something in the kernel. But purely non-symplectic, then G cyclic is a cyclic subgroup can be identified as a cyclic subgroup of C star. And so that, let's say, G is isomorphic to mu M with M the order of G. So, in fact, so we will, in the cycle, talk most of the time actually about symplectic automorphism. So, actually, all the case when G is equal to G0, so they don't have a non-symplectic action. But in fact, when you study automorphism, it's very natural to split the study in the two parts, symplectic and non-symplectic, that moreover behave quite in a different way. And one first proposition that is quite interesting. Take SK3 and assume that you have a group acting on an automorphism non-symplectic on it. Then, well, I was telling you last time when I started the chapter on automorphism that for the moment I was saying, okay, take any K3, not care very much about projectivity or not. Then now, if you have a non-symplectic automorphism, so this definition you can define for projective or not, does not depend, then you know that your K3 is always projective. And I mean, always finite order, okay? So I have all the, this is also important. Then S is projective. So I give you an idea of the proof since, well, in the lecture of Julien, he talked about Kodaira projectivity criterion and use it in this proof. So let's do just an idea how does it work. So idea of the proof. So the idea is that to use Kodaira embedding theorem, we want to find a rational Kähler class. On S. So we use an out2 factor. So we know that we have that H2 SQ is dense in H2 SR. And the Kähler cone, second fact. So the cone of Kähler classes. Yeah. So, sorry?
When on your remark, you say that if J is finite at purely non-symplectically,
yeah,
it works also if they act non-symplectically without the purely.
What I say, if they...
Like if the J acts non-symplectically,
yeah,
we doesn't ask that the alpha F is chromatic.
right, yeah.
It works also. We have also J additive.
This one?
Yeah.
No. No, because take, for example, automorphism for the 4, for example, yeah? And there are examples where it acts as -1 on the 2 form, just -1. Then you do sigma square. It's not identity because for the 4, but it acts as the identity on the 2 form. So it's, if it is not purely non-symplectic, it does not work, because then this means that the action on the 2 form is by a root of unity, but not a primitive one. So if I have order 4, it acts with the root of order 2, take power, then are symplectic automorphisms that are not trivial. So you have something in the kernel. Yeah. So, okay, and the other property is the Kähler cone. So the cone of the Kähler form is open in H11R. Okay, think about how is defined a Kähler class. So with actually a Kähler metric, so it's strictly connected to a Kähler metric, and Kähler metric is strictly connected with a positive definite Hermitian form, so that positivity is somehow an open condition. So this tells us that there is a C in H2SQ that so this is that we can decompose. Let's say better like this. We can decompose on H2SC. Decompose. We have the Hodge decomposition in that case to, well, you know, a 0,2 part or 2,0 part plus C11 part plus C02, where this one is a real Kähler 1,1 form. But when you look at C in H2SQ, well, it's rational, but you don't have this decomposition here. Okay? So now the idea is how can I modify C to kill that 2? Because if I kill that 2, then, well, I know that that is rational. And I use the automorphism here. So let's say how to kill the 2,0 and the 0,2 part. So use the automorphism. So observe here that since I had the question, that this proposition is for all non-symplectic, okay? Not only purely non-symplectic, but non-symplectic. So you will see the proof now. So how to do that? Let me use the automorphism. So I will consider the sum. Or maybe even, sorry, I just want a group acting non-symplectically. Just wonder if, well, no, let's say as we did, fine. So, okay, let's do like this. How we use the automorphism? So we consider the following. H, which is the sum of sigma star I of C for 0, the order of G minus 1. Then H is sigma invariant. Which is important. Okay, but now observe what happened here. Okay, it's sigma invariant, so I'm just working on C, so on that, and I take the sum. So the important is I have something invariant. And then remember that our automorphism and the powers also respect the Hodge decomposition. Okay, so this means I can decompose C in that way, one invariant part here, one invariant part here, one invariant part here. But you know that in H20 and H02, I don't have invariant classes. H is sigma invariant, so that H is equal to, well, I write simply H11, since H20 and H02 does not contain invariant element. Okay, because anytime, well, you look at the generator and you apply sigma, and you cannot have something which is invariant. So you're left with something which is still rational. The class is still rational. So I just apply an automorphism that and has no 2,0 part and non-0,2 part. But that means that this is rational. And we have that H11 is unequal to H and live in H2 SQ. And remember, so this is a Kähler form, and an automorphism send a Kähler form to a Kähler form. So this means this one part is really a Kähler form and is rational. So that a Kodaira embedding you take some multiple of this, of course, is an integer, and give you the embedding. And again, if some of you work on hyperkähler manifold, for example, well, everything goes through. So you can replace K3 by irreducible homomorphic symplectic, and that's work exactly in that way, so that you have the same definition and the same proof here. Okay. Just some quick example. We had some yesterday during the exercise section. So I give you an example for all of the three kinds. So first example, let's say one example of a symplectic automorphism. So well, we have seen this yesterday. E0 to the 4, x1 to the 4 equals 0 in P3C with iota sending x0, x1, x2, x3 to x0, x1 minus x2 minus x3. So we have shown yesterday in the exercise section that it is symplectic. And we have seen also that the fixed locus of iota on x4 are 8 points. So this is an example of symplectic. So just write down the two form and do the computation, and you see that it is invariant. An example of a non-symplectic one that is not a purely non-symplectic. So let's think about yes, yeah, that one. Again, always on the safe surface. Take x4 to, let's say maybe e1, since I have well, yes, iota 1, so it's okay. Take iota 2, acting always on x4, and iota 2 send x0, x1, x2, x3 to x0, I x3, where I you can think is a fourth root of unity. Then again, do the computation on the two form. So take wedge dx3. With this equation, this is f4, df4, dx0. This is sent to, well, you multiply by e, so it's also 2 minus dx2, wedge dx3, df4, dx0. All of this in x1 different from 0. 0. So you see here an example of a non-symplectic one, which is not purely non-symplectic. If E2 has order 4, it's clearly 4 here, but the action on the period is just -1. So that when you take the square of this is still not trivial, it's even our automorphism here, but the action is trivial, so it's symplectic. And finally, purely non-symplectic one. Let me just give you, I like very much involution, so I go on with some involution. Of order 4, why not? E3, no, of order 4, take not involution, E3. On x4, acting in the following way, x0, x1, x0, x1, x2, and x3 goes to x0, x1, x2, and x3. And I multiply the last coordinate by the fourth root of unity. Then again, you do the computation there, and then you have that E3 acts purely non-symplectically. And if you remark here, so the fixed locus, and so yesterday we discussed very much about fixed locus. So let's look at this. E3, x4, well, just put the last coordinate equal to 0. There is one isolated fixed point and a plane in P3, but the isolated fixed point does not belong to the equation. So it is x0, 4, plus x1, 1, 4, 4 equal to 0, which is a plane curve of genus 3. So I say in the projective space you fix a plane and a point, but this point 0, 0, 0, 1 is not on x4. So you have a curve of genus 3. And what you say in in example 1 and 3, which is you see you have different kind of fixed locus. So in the first case you have isolated fixed point, and we will see that involution symplectic also have 8 isolated fixed point. On the other hand, when you start studying non-symplectic automorphism, purely non-symplectically, then the fixed locus can be actually anything. You can have curves, you can have points. We will see that maybe today. Okay, so that's were some example. Let's go now to symplectic automorphism. So unfortunately, I will not have the time to explain, so I had to do a choice. Either I talk about symplectic automorphism or non-symplectic one. And well, I decided to talk about symplectic, because if you go to non-symplectic, there is a bit, some different things are different. So some are the same, but some are different. So let's talk about symplectic automorphisms. Okay, so are those that finite order preserve the two form. So there is a very useful proposition. Again, I will just talk about yesterday very fast, but let me formulate properly, which is the following. Take well, I take a K3 because I'm working on that. So take a SK3. Sigma acting on S, an automorphism, any for the moment, of finite order. Again, S does not need to be projective. You can be any, and you can even replace S but by a compact complex surface. You don't even need K3, but maybe at least for one part of the statement. So an automorphism of finite order, and let P in S a fixed point for sigma. So this means, so let me recall just some definition, that this belongs to fix, I was not overusing the same notation, but let's do like this. This means, so the point in S such that Q equal to Q. Then at such a fixed point, you can change coordinates. You can look at your automorphism locally, and locally you can find coordinate so that sigma is given by a matrix in the general linear group. Then there exist coordinates around P such that Sigma is given by the following. So that sigma is given by the following. So around P, sigma is given by a matrix in GL to C. So you can linearize the action. Okay, to remark about that, so it's a small lemma that one can show by using, one can find an ad hoc change of basis. And if you do using the Jacobian of the automorphism, and one important fact is automorphism is finite order. Okay, if you have no finite order, this is no longer true. This is even an important problem to linearize the action of automorphism is really something not trivial. But for finite order works, and to remark, you can say even more about that. So that's why I put K3, but anyhow. So since sigma has finite order, so M is finite order, plus sigma acts symplectically, then sigma, well, is equal to M, and you can diagonalize this M. So anytime you have something of finite order, you can diagonalize it. And this is lambda 0, 0, lambda conjugate with lambda n root of unity, even, well, unity, like this. N root of unity, where order of sigma is equal to n. So it's a n root of unity, not necessarily, of course, primitive. So it depends. And in fact, we have no, sorry, I will say something wrong here. Of course, this is primitive because I'm assuming order of sigma equal to n, and well, here I need primitive, something like that. No, I'm getting confused. It's primitive if the order is prime, but I'm not assuming anything, so that's fine as I wrote. In fact, we have, I wanted to say, I lost my, okay, in fact, we have, why this fact? In fact, we have that sigma star on the two form, so I mean that coordinate x and y, or let's say, just to fix the notation, x and y. Sigma star of dx dy, this is my two form, is equal then lambda bar, which is equal to 1, dx wedge dy. So that's why you need this shape locally. And the fact that you have that one, okay, we are always assuming that the sigma is not identity. Of course, if it is the identity, there is not very much to say. But this has also some consequence on the shape of the fixed locus. Let me formulate in, again, in some proposition. I'll tell you some information more about the fixed locus. So following proposition. So this local form tells you that, again, sigma acting on K3 S K3 symplectically, and sigma of finite order. Then sigma has only isolated fixed point. So no curves. Since the example I was giving above, you cannot have curves. Then we showed that, in fact, well, I was actually not telling about that at any moment, that the fixed locus of sigma is always not empty. You can have automorphisms that have empty fixed locus. We won't talk very much about that, but for example, you remember at the beginning we were recalling the classification of surfaces, and I will tell you about Enriques surfaces. So Enriques surfaces are quotient of K3, and these are quotient of K3 by an involution which has no fixed point. So there are such automorphisms, but necessarily these are non-symplectic, because the symplectic one always have something. If they respect the two form, then always have a non-empty fixed locus. And if I denote by n sigma, the cardinality of fixed sigma, that we know that we have only isolated fixed point, then this is less or equal than 8. You cannot have more than 8 isolated fixed point. So the proof, the first one is easy, because, well, look at the local action. Okay, so of course I'm assuming sigma not the identity, otherwise. If you assume this local action, but so this is affine, this is a copy of C2. So if you look at what fixes in C2, well, only the origin, only 0, 0. So since so in local coordinate, sigma is equal to lambda 0, 0, lambda bar, lambda different from 1, and only 0, 0 in C2 is fixed. In the non-symplectic case, what happened is that, again, using the action on the two form, you will have cases where you have 1 and lambda, for example. And then when you have, of course, eigenvalue 1, you have a direction that is fixed, and this corresponds, for example, a curve. But not in the symplectic case. To show this, we know to recall the Lefschetz number. That is one of the ingredients that one uses very much when studying automorphisms. So the Lefschetz number has the following expression. To use the Lefschetz number. Which is the following. L sigma is equal to the sum over all I from 0 to 2 minus 1 or j, let's say, many I, power j, the trace of sigma star on hi os. So the cohomology of hj. So and well, there is also a way to express L sigma. This is a Atiyah-Singer theorem, but we don't need it, so I will not, it's quite complicated, write it down, that express this in function of the curves and point in the fixed locus, but we don't need it. The important fact is now we want to compute that, because then if you know that the Lefschetz number is not 0, then you have point in the fixed locus. So let's look at that. Well, we have the trace of sigma star on H0 OS minus the trace of sigma star on H1 of OS plus the trace of sigma star on H2 OS. Okay, we don't have to care about the H1 because it's 0 for a K3. So this is 0. These are the constant. So here we have just 1. And let's look at this. So again, this is a third duality, H0 omega 2 of S. But here we know the action. The action is just identity. Okay, so just 1. Is one dimension, is 1. So I have 1 plus 1 is equal to 2. So L sigma not 0 implies fixed point in the fixed locus. And I say this is also again a theorem that is much more general. It does not work only for K3, but any compact complex surface. So L sigma not 0, and one part of this Lefschetz theorem in this talk about Lefschetz number. So or better, what say Lefschetz number is that when L sigma is not 0, then fixed sigma is a non-empty. Okay, in fact, so if you think about non-symplectic involution, you get a 0 here, and so that's why when you do having non-symplectic involution, you can have empty fixed locus, and in fact, you have it when you do Enriques. Okay, let's now think about the number of fixed points. You have the following, that 2. So now I need the other form of Lefschetz number, the 3. So we know that now 2 is equal to L sigma. And now, as I said, I can write down this Lefschetz number as a result of ATI Singer in function of the action of the automorphism on the tangent space. So this is the sum for the point in the fixed locus of sigma of 1 divided, so these are isolated, so that's very fine, of the determinant of the identity minus the action of sigma on the tangent space. So I write down the tangent space of S at P, so identity Ts at P. Remember, we look anytime we look locally at a fixed point. But now we know how sigma looks at a fixed point, okay, because we know it's still there somewhere. So this is nothing else that sum P in fixed sigma 1 divided by. So let me write, since I wrote always lambda bar, but of course this depends on the point. So this is 1 minus lambda times 1 minus lambda bar, and let me put a P here because I do a sum, and of course this depends from the points where I am, so which kind of stabilizer the point has. So that's why I write lambda bar P, and one can easily see that this is bigger or equal than number of fixed point divided by 4, since 1 minus lambda bar P, this is less or equal than 4. Much easy computation. You do that is less or equal than 4 because lambda bar is equal to 4. And so one gets that n sigma is less or equal than 8. So you have an estimation of the number of fixed points. Let's now see what happened for the prime order. So we'll do some computation that give you the right exact number when the order is P. Sorry, there are many P. P is the point, and P is the prime order, but anyhow. So that's the following theorem. following theorem. This was on a computation by Nikulin. I already cited several times Nikulin, but here will come even more somehow, because he was actually the first one starting the study of automorphism of finite order on K3, and then he started computing the fixed point and many properties of classification also, which kind of group acting symplectic you can have on a K3, and then also the people extended the result. So, but, well, he did in the prime order case, so sigma on S, order of sigma is equal to P prime, so it's not the same P as there, and sigma symplectic. Then, well, the theorem tells you two things. Which is the prime order possible? So one can always ask, well, I have an automorphism of finite order, symplectic or not, the question can be asked in general. How big can be the order? And maybe the first automorphism to check are the automorphism of prime order. So we ask in the case of symplectic automorphism. And we will see that it is 2, 3, 5, and 7, no more. And the number of fixed point is 8, 6, 4, and 3. If I'm not wrong here. Yes. So we'll do again using some technique that actually we have seen already, but quite useful. So first of all, observe the following. So first we remark the following. Proof. So we studied the quotient. S modulo sigma. One first interesting remark, so you have prime order, is that the singularity in the quotient are only AP singularity or AT singularity. So S has only even AP minus 1 singularities. It doesn't look like this directly. Well, again, I consider the local action. One can see it very fast. Local action at two coordinates x and y are always the same coordinate. This is lambda x, lambda bar y, with lambda primitive. This is true p root of unity. Since it is a prime order, I don't have to care about primitive or not. Well, any root which is not 1 is primitive. Now, if I consider the ring of invariant, so I will, sorry, the same notation. So let's say maybe Z1 and Z2, or, well, anyhow, let me just keep the same notation, that's no better. Cxy sigma. I take the invariant. Well, anytime I have to take it to the power p, that's fine. Y to the power p. And then I have the product, is x and y. Okay. And I call these new coordinates. 1, zeta 2, and z3. So with we have a relation that z3 to the power p is equal to z1, z2. So z3 is equal to z2. And if you make a change of coordinates, so just replace z1, for example, from z1 minus z2, and z2 by z1 plus z2, this tells you that this is z3 to the power p, d1 square minus z2 square. And if you at some point of your life, you study singularities of surfaces, this is AP minus 1 singularity. Okay, for example, for p equal to 2, this you find again A1. Okay, p equal to, we have an E1, which locally looks like we said yesterday. Well, we don't say the exercise, put in the exercise like this. If p equal to 3, let me tell you, I can still draw a picture for p equal to 3. So this is an A2 singularity. It's look like this. I should try to. Okay, it's a singular point. So you get this and so on. So the AP minus 1 singularities, which is somehow are the most simple singularities that you can have when you study surfaces. So again, here is the computation I did for K3, but this is independent, of course, if from KT surfaces. And any time that you have such kind of singularities, so and an AP minus 1 singularity is resolved by a chain of p minus 1 rational curves. So minus 2 curves. So I have something like this, p minus 1. Any copy is then a p1 of this, so and it is minus 2 because rational curves on a K3 is an intersection minus 2. So let's now consider the following diagram. To compute the number of fixed points, we use again one technique I use several times. So just use topology again. So I need two ingredients actually: topology and the fact that when you do the quotient of a K3 by a symplectic group of automorphism, you get again a K3. So consider the diagram. So here you have S with your action by sigma. Then you take the quotient by sigma. So you have n sigma fixed point. And here you have n sigma AP minus 1 singularity. Then you take here the minimal resolution that I denote by Y, for example. And we use the following fact, is that Y is K3. So essentially, for example, for the two form, you have this two form of the canonical divisor. Since, or the two form is even better, since you have this symplectic automorphism, it preserves it. So you go to the quotient, and then the quotient only AD singularities, and then you can pull it back to a form that is never zero here. So when you do quotient by symplectic automorphism group, finite, you get always K3 surfaces, which is again not the case if you consider non-symplectic automorphism. So we use that and then use topology. And we compute the Euler characteristics. Observe that that is also an important point, that between S and Y, we have a P to1 rational map. So this means if you take away the point here and the curve here that come from the singularities, this is a P to1 map. This is also P to1. Okay, that's good because the order of sigma is P. So let's compute the Euler point characteristic. It's very similar, the computation. So now it's not Coomer surface, it's NK3. But for example, for Coomer surfaces, well, when you started with the torus, and here we have two, yeah. But here we have a torus, there you have a torus and a K3. But here we have K3, K3. Yeah. Okay, let's compute key of S minus the fixed point is equal P times the key of Y minus in the curve in the resolution of the AP minus 1. So let me write down it that way, minus rational curves in resolution of AP minus 1 singularities. So now, again, easy computation, compute the key of such a graph. I don't know how, I will not say AP P minus 1. Well, yeah, because sometimes there's a confusion between the singularities and the graph. Okay, you say it's an A2 singularity, and then you identify A2 with that graph, or A1 with that graph. So this is, but I don't want to make too much confusion. So key of graph, let me write in this way, of AP minus 1 singularities. So this means, sorry, I'm not very precise, means that this is the key, the topological key of the graph of the curves. Then you can compute it because you have P minus 1, P1 that meet in P minus 2 points. Okay, you have P minus 1, P1 meeting in P minus 2 points. So when you compute the key top of this, you have, of course, 2 times key of the curves, but anytime you must pay attention not to count too much the point, not count this too many times. So this is, if you compute it, 2 times P minus 1 minus P minus 2. Okay, because when I compute this, otherwise I count some point, you see, I count this point 2 times, so I have to take once away. And this gives me, let me see, I'm lazy, is equal to P. So again, so this is, let's go back here, key top of S minus fixed point is 1, so n sigma, which is equal then to P times key top of Y. I write for the moment, then I know that it is 24, minus that one, and I have an n sigma. So P times n sigma. So I know this is 24, and I know this is 24 because I say this is a K3 surface. And if you put all together, this tells you that n sigma is 24 divided by p plus 1. So don't do all the computation. Is 24 divided p plus 1. Sorry, I remark now that, sorry, I forgot this p. That's why I was wondering. So this is, this comes from that p that I was forgetting. P times n sigma times p. So I think it's correct. And then 24 divided by p plus 1 is the number of the fixed point. And let's now check what can happen to decide the order of the group. Oh, sorry, I saw now that okay, just I stopped because I think, so we know that this is smaller than equal than 8, right? Or I just, yes. And then we compute, well, after the break, sorry, I was going over time. Sorry.